This is Geometry Lesson 10.3. We're going to be looking at the relationship between chords and arc measures in circles. So remember that we have a chord, which is a segment that has endpoints on a circle. So we have a chord here that's down here low. It's just from one point on a circle to another point on a circle. And then we have very special chords, and this is a very specific chord, and this chord goes through the center of the circle. Since it's very special and this chord goes through the center, it has the name of diameter. Okay? So we have a diameter is always when the chord, meaning it has endpoints on a circle, goes through the center of a circle. And we have intersecting chords, where we have here just some random chord that is intersecting the diameter. Okay. These create angles, the angles of intersection. They create arcs. These are not central angles here because they're not intersecting at the center of the circle, but there are angle measures when these chords are intersecting, and there are arcs that are created. So we're going to talk about those different things today. So congruent corresponding chords theorem, and this is saying when you have two chords of equal length. So in your handout right now, I want you to draw an arc that goes from one side of the circle to the other, and then using a little piece of paper, make a second chord that is the exact same length somewhere else in the circle. So you're going to draw two chords of equal length. Okay? You pause the video each time I tell you to do these things. Do that and draw that in here. So here's mine. I drew an arc, I drew the chord AB, and I drew a chord here, which I'm labeling CD. All right? And I took a little piece of paper and I held it up and I measured so I'm not using a ruler, I'm just taking a piece of paper and saying how long is this one and this, and they're exactly the same length. So I put my congruency marks on them. What happens is I can now, from endpoint D to the center of the circle, I can draw a radius. And that's the radius of the circle. The radius is constant to any point, which means if I draw the radius to the other three endpoints, to endpoint A and B and C, I end up with triangles, two different triangles, and we've got this chord here, AB, and this chord DC that are congruent. All of these radii are the same length, so I'm going to put one tick mark in each one of those, and then I look at each of those triangles and notice, oh, each of these triangles has exactly the same side. So by side congruency theorem, I know those triangles are congruent. And because they're congruent triangles, by corresponding parts of congruent triangles are congruent, by CPCTC, this angle here corresponds to this. They're not vertical angles, but they're corresponding in congruent triangles, and therefore those two angles are congruent. And those now are central angles because the vertex is the center of the circle. And these are congruent central angles, which means their corresponding minor arcs must also be congruent, because we learned that in lesson 10.2. That when central angles are congruent, the corresponding arcs, minor arcs, are congruent as well. All right, our next one, you have the second picture on your handout. I want you to draw a diameter, so that means a chord that goes through the center of the circle. Okay, so there's my diameter, and I labeled it EG, endpoints E and endpoint G. And then we're going to fold. You're going to take your paper and you're going to take this point G and you're going to fold it so that G lines up somewhere on the diameter. Not all the way across, but just fold your paper so that this point G lands somewhere on this diameter. And then fold that and make a nice crease. And what will happen is the crease will be perpendicular to the diameter. Okay, I'm hoping you've done that. And now we're going to draw that chord along that crease. Now I drew my chord. I labeled it DF, and I know that it's perpendicular because the way we folded that, we got a perpendicular line. And so we've got two chords, one being a diameter and one just being a chord, not a diameter, and they are perpendicular. And I'm labeling that point of intersection point H. And similar to the last circle, what I want to do now is I want to draw, I could draw triangles. I could draw it using a radius. I could draw, but we're just going to compare the length. So I just want you to compare the length from D to H using a little piece of paper. Just see how long that is and compare it to this length and see what you notice. What you should notice is that they are congruent. They're going to be congruent. And therefore, I shouldn't say, and we also could notice because we could fold the paper on the diameter here and fold it across, and we would notice that this arc here lands right on top of that arc, and those are congruent as well. We could examine this further by drawing, and I'm going to do this kind of quickly here. I could draw radii, and then we could talk about the fact that we're going to have hypotenuse leg theorem, and those are congruent triangles, and so once again I'm going to have central angles, and so the corresponding, because this then would be a central angle, and then this angle and this arc, we have the same measure, and the same thing with this angle here and this arc. In your third one, this is the perpendicular chord bisector converse, which says this time draw just a random chord. Just draw a chord. And we're going to label it TR. And then what we're going to do is we're going to fold the paper to create a perpendicular bisector of TR. To do that would be to fold T right on top of R. So you're going to fold your circle until the point T lands right on top of R. And then crease that fold. And what will happen is you'll know that since you folded T on top of R, you folded it in half. So we found a midpoint. And because this chord will land on top of itself, it will be perpendicular. And what you notice is, oh my goodness, it went right through the center of that circle, which means the perpendicular bisector of a chord is the diameter. That perpendicular, the one that we created, is the diameter of the circle. So, using those laws, we're going to find some information here. It says, use congruent chords to find an arc measure. Okay, so we've got here an arc, MN, and we have another arc over here, ST, and we're just going to find the measure of MN. We know that this arc over here is 112 degrees. Since the circles are congruent, the segments MN and ST are segments MN and ST are congruent, then the measure of the arc MN must equal the measure of the arc ST, and therefore MN is equal to 112 degrees. This went back to the congruent circles and congruent arc theorem. Using a diameter, okay? We're going to find AF. We're going to find the length of AF, because it doesn't have the bar over it. So it's saying find the measure of the segment AF. Doesn't have an arc, doesn't have an angle. It just has the letters AF. That means find the length, the measure of the segment AF. All right. Well, we have congruent arcs. We've got congruent segments. We know that AF is equal to the measure of AF is equal to the measure of BF. The length of the segment AF is equal to the length of the segment BF. And since BF is 13, AF is 13. And we've got congruent arcs. Since our chords were congruent, we know our arcs are congruent. And therefore, since they're congruent, I can set those two expressions equal to each other. We can solve for x. And then take this x, and we want to know the measure of arc DB. So we're going to plug it right in here to 5x plus 3. and we find that the measure of the arc dB is 63 degrees. And this was because we had congruent segments, which also gave us congruent arcs. I mean, I shouldn't say it's the chords, but this isn't a chord, this is a segment, and it's a segment to a perpendicular, so we've got that. All right. Congruent chords if and only if the chords are equidistant to the center of the circle. Well, when I say the equidistant, we always say perpendicular distance. So if you look at this diagram here, we're not saying from end point to the center. We're saying perpendicular distance to the chord. Because that's what, when it says chords being equidistant to the center of the circle, is saying that this distance right here, EF, and this distance, EG, are the same distance. And we can show this. We can show that this is true by drawing the triangles that go with them. And we would find out that we would have, again, if you draw your radii and you do this, we're going to end up with congruent triangles, and then congruent triangles by CP/CTC, all their corresponding parts would be congruent, and therefore their altitudes, which those would be altitudes, would be congruent. So again, once we could find those triangles are congruent, their parts would be, and therefore we can see that they are going to be equidistant. Now that also means if they are equidistant, then the chords themselves are congruent. So this is one that we're going to use a lot of. When we know that chords are equidistant, we know that the chords therefore must be congruent. Okay? That's if and only if, means either way. All right, so here we have a bunch of stuff going on. Using congruent chords to find the circle's radius. Well, the circle's radius, remember, it would be this right here, this QC. That would be the radius, okay? And we want to figure out what that is. And we're looking at a bunch of stuff that's going on in here. And we see that we have this perpendicular distance to the chord QR is 4x minus 1. And we see the perpendicular distance from ST to the center, from the chord ST, is 2x plus 7. And it's telling us some other information. It's telling us that the length of QR is the same as the length of ST. So we know that these two chords, this chord here, QR, and the chord ST are congruent. And if the chords are congruent, then we know that these distances, 4x minus 1 and 2x plus 7, must be the same. So we can set them equal to each other and solve for x, and we get x equals 4. So now we can figure out what that is right here. We could plug in that 4 into 4x minus 1, and I can find out that that distance is 15, so I know that this is 15. And look at this right here. QUC, that's a right triangle with one leg of 20, and one leg now we know is 15. And we can use the Pythagorean theorem, or we can see that we have a 3, 4, 5 right triangle that's been multiplied by 5. It doesn't matter which way you figure this out, whether you use Pythagorean theorem, 20 squared plus 15 squared equals r squared. So then take the square root of that and you get 25. Or you notice that there's a ratio. This is 20 and 15. These are both multiples of 5. And you go, oh, it's 4, 3. Then that's got to be 5 times 5. So you can find this out by using the 3, 4, 5 right triangle. There's some classwork problems that go with this lesson, so I'd like you to work on those, and I'll be checking your classwork for both lesson 10.2 and 10.3.